Hello everyone. In this video tutorial, we'll explain when it is required to take J option during selection of a solution phase in Factsage calculation. J option is selected by default for a phase which has more than two possible miscibility gaps. Most well-known example is when titanium niobium containing carbonitrate phase forms along with iron austenite phase. As titanium carbonitride and niobium carbonitride have FCC crystal structures, therefore during modeling of this kind of phases, same FCC phase model is used, which is also used for austenite phase modeling. Therefore, in order to do a proper calculation in Factsage, the J option should be applied for selecting this FCC phase. In this video, we will calculate and show the selection of J in during calculation, and to do that first we have to open Factsage. As we open Factsage, we have to do all this calculation in equilibrium module. To open the equilibrium module, we have to left mouse click on this equilibrium button. When the equilibrium dialog box is open, we have to first select the data base. So for this calculation, to select the database, we have to go to data search and left mouse click on this data search. For this problem, we'll select FSTL database and will not take a fact-based database because no gaseous phases or pure elements we are taking. So we'll unselect this one, and then after selection of proper database, we'll click OK. Now we have to add all the chemical species of reactants. To do that, we have to go to this plus button, which is add a new reactant button, and we left click on this. Now in our steel we have iron, and then as alloying elements we have titanium, we have niobium, we have carbon, and we have nitrogen. The iron amount for this example, we are taking 99.875 weight percentage, titanium 0.018 weight percentage, niobium 0.068, carbon 0.039, and nitrogen 0.01 weight percentage. After all the required data, the amount data, and the chemical information of the reactants are given, we'll go to the next window, which is menu window in equilibrium module. In the next window, we'll first select all the pure solids, which are the product phases can be formed in our calculation. So to select pure solids, we have to go to this white box and click left mouse click on it. As you can see, 23 species are selected, but in our case some of the pure compounds are not formed, so we have to deselect them. In order to do that, we have to go to this pure solids and right mouse button click on it. So in our case, S- Solid graphite and solid diamond are not forming in our products, so we will not select them, and we'll keep other pure compounds, pure solids, and then click OK. To select all the solution phases at once, we have to go to the select option and left mouse button click on it and click on select all solution. As you can see, all the solution phases are selected, and by default, three-phase immiscibility in FS steel FCC solution base is selected. Now we have to put the temperature range. The initial temperature is 600 degrees centigrade. The final temperature will put 1000 degrees centigrade with 1 degree centigrade as temperature interval for our calculation. Then after putting all the data in the file, we will put calculate, left mouse button click on it to calculate our thermodynamic calculation. After the calculation is done by FactSage, we get a result window, and here for each temperature we have the results of which phases are formed. So first we'll see that FCC A1, which is the phase #1, which corresponds to the austenite phase. The next FCC A1 phase is FCC A1 #2, which is actually niobium carbonitrate phase. Niobium is major component in here. Then the third FCC A1 phase is characterized as FCC A1 #3, has major element as titanium. So this is titanium carbonitrate phase. So now we want to visualize the amount of phases formed at different temperatures. To visualize that, we have to plot the amount of phases versus the temperature. To do that, we have to go to output and left click on it, and then click on plot, and then plot results. After clicking on plot results, this result window pops up. Here we have to select the axis to plot proper diagrams. In axis, we have to select the x and y axis. We have to first left mouse click on this axis button. In y variable, we have to select the amount of phases in gram which are formed. So we select gram, and then the minimum is 0 and the maximum is 100 grams, and then we'll take at every 5 grams. Also, in temperature, this is a lower range of temperature. This is the maximum temperature we have given, and we'll take at every 25 degree centigrade. So now all our axis informations are given in FactSage. Then we click OK. Then we have to select all the species which are formed. So to select them, we have to go to this select option and left mouse click on this button. Then these are all possible phases which we have selected as our products, but we have to select the phases which are formed. So go to select option and then left mouse button click on it. Then select all the stable phases in this calculation. 5 species are selected. Now We click on OK. So all the information which are required to plot the required plot is given. Now we click on left mouse button, click on this plot button. As we can see, FactSage have plotted the amount of phases with varying the temperature in x-axis. So as you can see, the austenite forms at high temperature, and as the temperature lowers, the BCC phase forms for iron. And also we can see some other FCC, FCC2 and FCC3 phase are formed, and also cementite phase are formed. But these phases are very low in amount, so we can't see the proper amount of these phases. In order to visualize properly, we need to decrease this range of y-axis. To do that, we have to go to this gram and left mouse double click on it. This frame and axis windows pops up, and then here we have to give the range at which we want to see this species. So we'll give maximum range to be 0.1, and we want tick at 0.01 and levels at 0.01, and we keep the y-axis range untouched, and then click on OK. Here this green line indicates FCC has two phase, which is NB niobium carbonitrate phase, as you have seen from the results. To put the text name, we have to go to text and left mouse button click on it, and then this is FCC2. We increase the size, put the proper color, and then click OK. This is FCC2, and this is FCC3, which is titanium carbonitrate phase. Similarly, to put text, we go to add label. This is FCC3, and we put FCC3. So this is how we plot the phases which are formed and the temperature range to visualize the amount of phases formed at different temperatures. Next, we will demonstrate how carbide and nitride precipitation occurs in microalloyed steels. Microalloyed steels are special grade of steels which are used for high strength applications such as pipelines. The superior properties, the superior mechanical properties are attributed to the precipitates which are distributed by using thermomechanically treated alloys. Now, FactSage can be used to find the correct temperatures for these thermomechanical treatments of steels. For this thermomechanical treatment, the steel is annealed in the austenite region and then continuous cooled from austenite to ferrite region, and this corresponds to the air 3 and air 1 temperature. The air 3 temperature corresponds to the ferrite transformation start, and air 1 temperature corresponds to ferrite transformation finish temperature. The objective of this exercise is to Find the ideal annealing temperature to avoid detrimental niobium carbonitrates formation and to promote and facilitate the beneficial niobium carbide precipitation. In this exercise, a typical microalloyed steel composition as shown here is entered from this reference. Therefore, we'll first enter the composition of steel in equilibrium module of Faxage and do the corresponding calculations. As shown before, we'll first open the Faxage and then click on this equilibrium button to open the equilibrium module. After the equilibrium module is opened in this window, we'll select the proper database. To select the database, we'll left mouse click on data search and then we'll select FS Steel database and then click OK. Now we will enter the alloy composition. As per the reference paper, we have 9 alloying elements. We will enter them by adding a new reactant. Then we will enter the chemical formula of the species. We have iron, carbon, manganese, silicon, titanium, molybdenum, niobium, aluminum, vanadium, and last nitrogen. The iron composition is 97.935 weight percentage, carbon 0.039, manganese 1.51, silicon 0.08, titanium 0.018, molybdenum 0.28, niobium 0.068, aluminum 0.011, vanadium 0.05, nitrogen 0.0095 weight percentage. After putting all the weight and chemical species information, we will go to next. In this window, we will select all the product species as we are interested in carbide, nitride and carbonitrate precipitation. So we will select all the solid compounds. To select all the solid compound species, pure compounds, we have to go to this square box and left mouse click on it. We have 124 species selected. Now we have to select all the solution phases. In order to do that, we have to go to select, click on it with left mouse button and then select all solutions. Now here we have FCC-A1 as 3-phase immiscibility. Similarly, we'll put J option 3-phase immiscibility for BCC and HCP phases because carbonitrates have similar structure to austenite. We'll we'll right mouse button click on this area and then select possible three-phase immiscibility. We'll go to HCP and right mouse button click on this area and select three-phase immiscibility. And then for all the carbide phases, these are the carbide phases, we'll put I option, which is two-phase immiscibility. So after putting all the FCC, BCC and ACP phases as with J option, which is three-phase immiscibility, we add all the carbide phases to be two-phase immiscibility. So to do that, we'll go to each carbide phase and right click on this area and change it to possible two-phase immiscibility. So after all the carbide phases are changed to from single phase to two phase immiscibility, we will add the temperature range, which is starting from 500 degrees centigrade to 1600 degrees centigrade as final temperature, and with 5 degree centigrade as interval. We are selecting from 500 to 1600 degrees centigrade to cover the whole temperature range encompassing the austenite phase. So after doing all these additions, we will go to calculate and click left mouse button on calculate option. So there are a lot of phases we have taken, so it will take some time to calculate. Now we are done with the calculation, so we want to see all the found phases at different temperatures, and to visualize it properly we have to plot the gram of each found phases corresponding to the temperature range. And to do that, we have to go to output and left mouse click on it and then go to plot and plot results. We click our left mouse button on this plot results. Now this result and axis pop-up window is opened, so we have to select the axis to give the proper x and y axis data. So to do that, we'll click on axis button with left mouse click, and in y axis we'll plot the gram of each found phases. To do that, in y variable click on the left mouse click and select the gram, and in x variable we'll put the temperature range. So temperature is temperature in degree centigrade and as the temperature variable as x. So now we'll refresh, and then after putting all the x and y axis data we will click on OK. Also we have to select the species which we want to plot, and in order to do that we'll go on select option and click left mouse button on this. So now this window is opened and we will select all the possible stable phases. To select that, we'll click on select and select all stable phases. Now our 12 species are selected. Then we'll click on OK. Now all the information is done. Now we'll click on plot with left mouse button click. So now this Faxage figure module has plotted this graph, and here a lot of information is there. So first, from this graph we can easily see the Freyright transformation start temperature, where the austenite from austenite the ferrite starts to form. This is AE3 temperature, which corresponds to the ferrite transformation start temperature during continuous cooling, and this temperature corresponds to AE1 temperature, which is ferrite transformation stop temperature. But also we have to look at the very low compositions, since all the microalloyed elements will be present in very small quantities. So we have to change the y-axis range to see, to visualize the micro constituents which are formed properly. To do that, we have to go to this gram text and left mouse button double click on it. This frame and axis window pops up, and here we will change the y-axis range to visualize the microalloyed elements properly. In order to visualize in a more effective manner, we can change the axis and the y variable we should take gram but in log scale, and we'll change the range from -3 to 2 with ticks at 0.1. This will help us to visualize the formed phases properly. So now we click on OK, and then we click on plot. By doing that, we form this kind of diagram. So this contains a lot of information. Now if we take that diagram and properly mark all the phases, so here we see the AE3 temperature, this is AE1 temperature, and we can also see that the FCC1, FCC2 and FCC3 phases are forming. So in this case, these phases are probably carbides and nitrides, these FCC phases. So we can check and confirm this by plotting their composition with temperature, the composition of each these phases with temperature, and we'll do that in Faxage model, equilibrium model. First we'll select all the FCC #1 species in the FCC #1 phases and see how they are distributed. To do that, first we close this figure model, and then in Access select the species, click on it, Here we have all the possible phases, and there we need to select all the constituents of FCC-1 phase. Also, we'll take out other phases which we have selected before. Here we'll taking out all the other phases apart from FCC-1 to see the phases, the constituents of FCC-1 phase. So after deselecting all the other phases and keeping the FCC-1 phase and its constituents, we are done. So we'll click on OK and then click on plot. So the figure module gives us this diagram. So if we tweak the diagram a little bit more, we can see this kind of diagram. So here we can clearly visualize that the austenite region, FCC-1 phase is composed of mostly iron, and you can also see that below AE3 temperature the dominant species are molybdenum carbide, titanium carbide, and niobium carbide. Similarly, if we draw the phase diagram and the constituents of FCC has two phase, we can see in austenite temperature it is mostly consist of titanium nitride and niobium nitride, and below the A3 temperature, austenite temperature, we have niobium carbide. Finally, if we draw similar diagram for FCC hash 3 phase, in austenite region we have primarily niobium carbonitrides, and below A3 temperature we have titanium and vanadium carbonitrides. Also, if we draw similar diagram for HCP hash 1 phase, there we can see that this phase HCP hash 1 appears below A3 temperature, and it is composed by primarily molybdenum carbide, vanadium carbide, and manganese carbides. Now we know that what are the phases of what are the constituent phases of each phases which forms, and it is really convenient to plot the species of interest, which is mainly niobium, titanium, and vanadium carbonitrides. So if we copy the amounts of niobium carbide, titanium carbide, and the species contained in FCC hash 1, 2, and hash 3 phases, as well as the carbide and cementite phases in Excel, we can get the following diagrams, which clearly separates the different region of different type of precipitates. So here we can see the temperature region of titanium nitride, the temperature region of niobium carbonitrides, and the temperature region of niobium carbides. So from this diagram, we can figure out that what are the equilibrium phases which can be formed at each temperature region, and using this diagram we can design the thermal treatments which are favorable for the alloy which we are designing for the tailored application.